Welcome back to the Hyperbolic Coding Chamber. Yesterday we received an amazing gift from the LeetCode developers. We received a day free from LeetCode, sort of. So the website went down and no one was really torn up about it because daily LeetCode is kind of the worst. But fortunately, we got to do a little bit of LeetCode before the servers went down, so it do indeed be like that. So yeah. So now that we got that little break, now we're kind of being forced back into the crucible, and I heard there's a rumor floating around that they made the problems even harder. So every easy became a medium, and every medium became a hard, and there's now actually a new category of problems called unsolved. So granted, likely will solve all of the unsolvable problems because the HCC is a Discord capable of solving any problem, even the biggest questions of our time. So one of the problems we're working on in the Discord right now is the meaning of life. So if that's something you're interested in, I think we're pretty close. So you're probably gonna want to be in the Discord for when we figure that out and we blast the answer out to everyone. So this is a necessary evil, so who knows what will happen when this information comes out, but you can consider the Discord the open AI of philosophy. So yeah, we're gonna have another talk. We had a couple of people back in the VC yesterday. Tonight I think we're gonna have a lecture. Who did we have scheduled again? I think we're gonna have a lecture by 21 Savage. He reached out, he wanted to talk about he seems to be very, very interested in data structure problems. So, yeah, we're going to be having a lecture about that in the Discord. So if that's something you're interested in, you're definitely going to want to join. Followed by just a general jam session because he's kind of the GOAT. So, yeah, so that's what's going on. If you're excited about that, you should definitely join the Hyperbolic Coding Chamber, which is rapidly expanding to millions of new members today. So that's kind of how it be. Things are progressing well. We have days until the holidays, and fortunately, we're on break, so the grind has been a little bit easier. But also, I realize it's actually been sort of harder. So I think there's something to a schedule that is kind of important. So I'm still doing my time as usual, but yeah, it kind of threw me off because I usually do the same thing every day. I work for 8 hours and I do the LeetCode, and then the game dev, and then I chill, and then I do game dev again afterwards. And then the first day kind of threw me off because I was just getting all the rest back. And then, yeah. Also, yesterday I pretty much zonked myself out on all the content that is available. So, maybe man should not be left to his own devices. So yeah, I just spent like the whole day zonking out. I went from anime to YouTube to eating out to just chilling, but at the same time, I don't know if it's because just the way my brain is, I'm relatively certain this makes the grind harder because I'm mostly in all these things. The reason I think there's so much shifting around is because I'm searching for novelty, and then once the search for novelty begins, it always ends with just a bleak outlook because the brain chemically becomes nonsensical. So that being the case, we're going to have to crank up the hours done, but we do have kind of a packed schedule today in terms of family requirements. So we're still going to do our regular 2 hours because we're free from work, but I'm really excited about next week, Monday, where we'll just have the ability to just focus straight through. So hopefully that is coming soon, which it is. And yeah, I think we should be ready to jump into the LeetCode. So here we are again. This is my classic mix of music that we always use. Also, if we peep the LeetCode store, I think they got some actual drip that must be copped. But I'm pretty sure I don't have any Leet coins. Or I have 599 Leet coins. Oh wait, we actually have oh, you can time travel. Nah, I feel like the actual LC shirt is actual drip. It's actual drip. So We're gonna need to be able to maybe, if the LeetCode devs would actually give us one, that would be incredible. But this is actual drip and must be done. So maybe we'll get there 3 years from now. We'll finally be able to get the exclusive LeetCode kit. That's all this is about. This is literally about their shirt. So let me refresh the problem. I don't think I ever got to finish the problem I was on. It looks like it is indeed working again. So I'm just gonna jump into it. It does say, so let me click submit. I actually don't even know where we left off. I think what I was trying to do is optimize this problem. No, there's a portion that isn't solving, I think. Let me check. Right, so we do have TLE. And I was wondering why that was. I wanted to see. Yeah, we do have a lot of pairs to check. That is pretty crazy. But it's not as crazy given the input. I'm pretty sure if I don't print anything, this passes. But even so, it's kind of crazy that this code even takes that long in the first place. I guess it's capped. I guess it doesn't pass. I guess it's a little too close to the slow end. We're doing linear iteration, n squared, and then potentially another crazy amount. It's got to be a way to formulate this with two sum arrays. This one is so strange. I'm pretty sure if it'll work if we remove this nonsense we tried to do here. So we created the array beforehand, but now it just created issue. Instead of doing plus equal, we can just do push sub r sub I, and then instead of doing sum array sub I equals sum, we can just do push and add it on like this, and then similarly you can do unshift sum 2. This is supposed to say sum array 2. Wait, what is going on? I still have this line in here. So it works like this, but it literally takes forever. And now I'm realizing what we're checking here with the second IDX is just that the sum array in the second half also equals the sum of the remaining elements for the second index equals the sum. If that's the case, couldn't we also just check that here, because we're just pushing it on here? That way we could remove this nonsense here and just say and sum array sub m, right, which equals the secondary index. The index after it should contain the sum in sum array 2 of all the elements after that element. So if we say n sum array m equals sum array of m plus 1, but with 2, we shouldn't have to push any candidates on. We can just say return true, and we should be able to delete this and all of this nonsense. Or maybe not. Oh no, right, wait. The sum going backwards, so it should already exclude the value that sum array m. That's strange. This. Summary sub m minus summary sub I. Summary sub m is the value we're currently checking to see if it could be the partition of the array into the second sum. If it can be that index So think about the fact that I'm checking if it's equal to sum array sub m doesn't make any sense. Shouldn't it equal sum array sub I? This is much better. This literally shaved half the time off, but it's still ridiculously so. I mean, we're not really going in order of magnitude any order of magnitude faster. So we're doing a for loop here to check. Is there any way we can skip this for loop? Because we know that if we can generate a second pair, we can automatically check the third pair. And I'm realizing now the reason we have to have the two sum arrays is because when you're going forward, when you're going forward, it allows you to check if two subarrays. When you're iterating through forward, it allows you to check whether two subarrays share the same sum, because you can subtract for any index, right? That's in the first partition. That's going to be its sum, and then for the second index, you can just subtract the second index minus the first, the start of the second, the end of the second sum, the end index of the second partition minus the end index of the first partition to get the sum array, the sum of the subarray for the second partition. Then for the third one, we need to have an array that has iterated through it in reverse, so we can check the next element to automatically see what the sum is. Worst case, this has to be n squared. Now that I'm realizing, it just seems that n squared barely passes because we're going through the array but twice. So this is kind of like, yeah, so going through the array but twice. For each one, we check if it meets a particular value, and then we can return true. Space-wise, we're using linear space but twice. This one's kind of tough though. I don't see of another way that one could make sense of this problem. Sorting can't help because it would change the order of all the subarrays, which would pretty much change all the subarrays. I'm pretty sure divide and conquer could make sense here. If you started in the middle of the array and you had the sum array, maybe we could intuit divide and conquer. If you're in the center, we're looking for three indices such that sum array sub I is equal to sum array sub m minus sub array sub I, and sum array 2 sub j, or I guess j is the second partition, m, yeah. And let's just say m is the second partition and j is the third partition. That sum array 2 sub j equals sum array sub I. But I don't really know how divide and conquer works. I think you're only supposed to consider half of the subset. Or something like that. I think you could also generate all subarrays, map them to a map where the index would be the sum that they equal, and the right hand, and it would have an array of tuples where each tuple would have a start and end index for the subarray. Then you could just iterate through all the pairs and check whether or not there are three indices or three pairs of tuples that cover the entirety of the array and don't overlap. This doesn't seem like it'd be faster though, because to generate all the subarrays, you'd have to do n squared, and we're already doing n squared now. So it'd basically be the same thing. I guess you'd get to cut out. Actually, would you get to cut out this portion right here? You would. I guess you get to cut out this linear iteration beforehand. Well, then you're just replacing it with checking all the... Yeah, this seems like the best option that we can currently come up with. Let me see. I wonder if we can come up with it with a hint. Any related topics. Greedy. Array. So maybe there's some general heuristic that we can make that will generally apply to the entirety of the problem. So does that exist? 021 negative 6679 1201 365 negative 2251 negative 4. Yeah, I think they might have us beat on this one. I can't come up with something that's not n squared. Maybe my last thing I'll try is maybe we can. It's also a greedy thing, but I don't understand how you'd make a greedy approach here. Just pick a group. If you just pick a group of elements. Give it an array of integers. Yeah. I don't think that this is it. I guess we should just look at the solution. Two of O of n time. Method 1. Count valid parts. Loop through the array A and compute part of sum. If the average value is found, reset the part to 0 and increase the counter. By the end, if the average can be seen for at least 3 times, and if the total sum is divisible by 3, return true, otherwise return false. A dot sum. What is this language? What is this? Array dot stream A dot sum part equals 0, average equals sum over 3, C and T equals 0. I guess in the sum equals this, which is just A summed, part is equal to 0, and they divide the average by 3. That would be the average value. Then they iterate over A, they say part plus equals A. If part equals average, find the average. Find an average, increase the counter. Then we reset the part. Then if the count is ever greater than or equal to 3, and sum mod 3 equals 0, if having found average values on both parts before the 2 pointers meet, alright, the 2 pointer solution here is really impressive. I didn't think 2 pointers could be applied used this way. But specifically, they're using a property I only considered things of the problem I only considered the structure of the problem as a potential part of the solution, but I never considered that we could derive some output, some total output like the average, and use that in our solution. So we created the sum array, which helped us, but I didn't think calculating the average or something like that would be useful. Interesting. Yeah, maybe the math guys, maybe the math dudes are just different. Because that, I don't get how they got there, but... now we have divisor game. Alice and Bob take turns playing a game, with Alice starting first. Alice and Bob take turns playing a game, with Alice starting first. Initially, there is a number n on the chalkboard. On each player's turn, that player makes a move consisting of choosing any x that is greater than 0 but less than n, and n mod x equals 0. For example, 3 mod 3 equals 0. Replacing the number n on the chalkboard with n minus x. Also, if a player cannot make a move, they lose the game. Return true if and only if Alice wins the game, assuming both players play optimally. If both players play optimally, I was going to say who goes first. If Alice goes first, so if Alice chooses 1, for example, 1, n is equal to 2, 2 mod 1 gives you 1. Then 2 minus 1 gives you 1. The number on the chalkboard is 1. Bob has no more moves. How does Bob have no more moves? Is there no number such that 1 mod that number equals 0? 1 mod 0 gives you what? 0, doesn't it? Or you can't do that. Oh, I guess you can't do 1 mod 0. But 1 mod 1 does give you 0. So how does Bob have no more moves? How does Bob have no more moves? Alice and Bob take turns playing a game, with Alice starting first. Initially, there is a number N on the chalkboard. On each player's turn, that player makes a move consisting of choosing any X On each player's turn, that player makes a move consisting of choosing any X, with X being less than N. I see. So you can never choose the number itself. Otherwise, you could always win. That's true. If the number was N, you could always just say N mod N gives you 0. The reason Alice chooses 1 is that she can't choose. The only number left to choose is 1. She chooses 1. 2 mod 1 gives you 1. And Bob he can't choose 0 or 1, so he loses. So basically, if the number ever gets to 1, you lose. Since you can't choose N, you lose. So if the number equals 1, you lose. If that's the case, maybe there's a greedy way to look at this. Assuming both players play optimally, assuming a random value like 32, you can't choose 32. So maybe the optimal value to choose is always N minus 1. If you choose N minus 1, you'd always get the person to 1. Wouldn't you? Because 32 mod 31 gives you 1, doesn't it? Gives you 4,000. Yeah. So can't you always just choose N mod N minus 1? That would mean that Alice wins all the time unless the number starts at 1. Alice chooses 1. Why does Alice choose 1? If we assume both players play optimally. Oh no, wait, I might be confusing it. What we do, if you have something like 32, if you choose 31, you have to choose a number between 0 and 32. You choose 31. Oh, and N mod X equals 0. I see, so you can't choose N minus 1. It looks like the best you can do, let me keep some information here. If N equals 1, you lose. N mod X has to equal 0, so you have to choose a factor of the number. So if the number is 32, the best you can do is choose like 8. Maybe when they mean optimally, the best you can do is choose the largest factor of a number that's not itself. So for 32, you could choose 16. If you choose 16 though, 32 mod 16 would give you 0, and then you can say place the number N on the chalkboard with N minus X. We have 16 remaining. All right, now what would B choose? The remainder now is 16. Largest factor would be 8. He chooses 8. 16 minus 8 would give you 8, right? Now A chooses 4. You have 8 minus 4 gives you 4. And then B chooses 2. 4 minus 2 gives you 2. Then A chooses – 4 well, you can always do 1, right? Because if someone had 16 mod 1 always gives you 0. I think any number mod 1 always gives you 0. So B chooses 2, right? And if 2 is left, then Alice can choose 1. But maybe there's no greedy option for optimality. 4 minus 2, you'd get 2, right? 4 minus 2, you would get 2. There's 2 remaining. Alice chooses 1, she would win. Because if Alice chooses 1, then 2 minus 1 equals 1, and Bob has no moves. But I don't think Bob played optimally, because why did he choose 2 here if he was going to lose? He could just choose 1 here. Bob chooses 1 here, then the future branches. And instead of doing 4 minus 2 here, we end up with 4 minus 1 with 3 remaining. If 3 is left, then the only thing Alice can choose is 1. Bob still loses. I think the only way to test this is to see if I put in 32 here, Alice should win. But I'm wondering if I did our calculations wrong and there's a way that Bob can win here if he plays optimally. I have to return some value to run this code. So it does look like Alice should win here. It seems complicated though. How do we know? How do we know that the optimal choice to make is always the largest number? This one has a lot of dislikes. I feel like the way to do this is with graphs. Feels like the shortest way to do this would be graphs. Issue is the edges between the vertices. What would those values even be? What would they even be? Alice and Bob, they chance playing the game with Alice starting first. Unless there's a number and on the chalkboard, each player's turn, the player makes a movement. You know. It feels like we could skip this though. I'm wondering if this problem is very simple at heart. But we need a way to confirm whether or not a greedy option makes sense. But I feel like I'm getting overwhelmed by the math of it. And we could write a greedy algorithm here, but I feel like I would just be guessing. If we just assume that if the optimal move is to make the biggest step they can make, then we can just toggle the value and see who gets left with 1 at the end. How large can n be? Up to 1,000. We would just be guessing. I'm wondering if this problem is really more involved, which is why it has so many downvotes. But it feels like if both players play optimally, is the part that is the question mark. Optimality either implies we need a graph, and optimal, where the nodes would be the vertices would be the choices the players make, and the edges would the vertices would be the actual game state, and the edges would be the choices the players make. And we would know if and only if Alice wins the game, assuming both players play normally, by doing a breadth first search on this graph and finding pretty much the shortest path to victory. If Alice is the one with the shortest path, but we could skip all that if it can be proven that the optimal choice is just a greedy choice of choosing the largest factor. I don't know. I'm going to guess and write the largest factor version. So given the largest factor of a number n, we're going to get the largest factor of a given number n. I don't know of a good way to do it, so I'm just going to do -1 means there is no largest factor, or the largest factor is either itself or 1, and we're basically going to start from let I equals n minus 1. I is greater than or equal, I is greater than 1, right? As long as I is greater than 1, then we want to keep going, right? I minus minus. And we'll say if n mod I equals 0, then we'll return I. And I think if we do something like largest factor of 8, and then we can do a couple more like 32, something like 1024, we should get 4, 16, and 512. And then for another test, I'm going to pass in 1, and we should get -1. So this seems to make sense. And then what we're going to do is just assume that both players always take the largest factor as their turn. And we're just gonna say let is Alice equals true, and we'll just keep flipping this value. Then we can return a value at the end based off that. So we pretty much have to go while n does not equal 1, right? While n does not equal 1, right? We're going to let the largest factor, we're going to get the largest factor for it. That's the move the player is going to make. We don't have to check and do n mod the factor because we already know because it's a factor. So we'll just do n minus equal f. And then we'll say is Alice equals not is Alice. And we want to return true if and only if Alice wins the game. So we can say return, so if is Alice, if the last value is not Alice, right? Because the last person to make a move always loses. So if it's not Alice, I think that's all we should have to return. So for example, if you run this for n equals 2, the largest factor is I forgot there's one more thing we have to check. Right. If f equals -1, it means there's no choice. There's no choice the player can make. If there's no choice the player can make, and the player is if there's no choice to make and the player is Alice, then it means they lost. There's no choice to make and the player is Alice, it means we're returning true. We should only return true if Alice, if and only if Alice wins the game. So if there's no choice to make and the player is not Alice, then we'll return true, right? Which is good. And then if we make it to the end, right, if n does equal 1 and the person whose turn it is I think it should be that. Just to make sure this is making sense, n equals a value, right? Alice chooses factor. New value is n minus equal f. So n equals n, right? I guess you can choose one. But if n equals 1, if there's no choice or n equals 1, you lose. N would never equal 1 though in this loop. So this outside loop is what's handling it. So if f equals 1, if you can't choose anything, then we need to return is, it might be easier to is Alice's. I think that's why this is a little hard to follow. My thing says is Alice. Is Alice what? So if it's Alice's turn, then she chooses this, right? Now, if she chooses -1, and it's Alice's turn, right? Then if she chooses -1, right? And it's Alice's turn, right? Then we have to return false, right? Otherwise, we can return true, which is basically the same as saying not. If f equals -1 and it's Alice's turn, return false. If it's not Alice's turn, it must be Bob's turn, which means that Bob has no choice and Alice won. If we're out here, it means that n equals 1. Now, if n equals 1, then we can copy the same case that we have here. And we'll say, if it's Alice's turn, right, it's the last turn of the game, we want to return false, she didn't win. Otherwise, she did. Yeah, this is not that simple. Maybe the game is that every optimal move you can make is just choosing the largest factor to get to 2. So once you get to 2, there's nothing if you choose 1. Wait, no. Alice chooses 2. Should she have not chosen 2? There's nothing else you can choose though. If she chooses 1, 4 mod 1 does equal 0, and you can do 3. If you do that, then there's 3 left. So there's 3 left. You can do 3 minus 1 would give you 2. 3 mod 1 would give you 0, and you could do minus 1 to get 2. Return true if and only if Alice wins the game, assuming both players play optimally. 1.7, 3.6. I wonder if this approach... We passed half the test cases. N equals 4. This, in my optimal choice universe, Alice doesn't win. They're expecting true, which means that there is a universe where Alice does win. In that universe, instead of choosing 2, the only other option is 1. She chooses 1. Then N equals 3. From there, Bob can either choose 2 or 1. He can't choose 2. He has to choose 1. And then even there, Alice still loses. So how does she win here? You can't choose N itself. She can't choose 4. She can't choose 3. She could choose 2 or 1. If she chooses 2, she already loses. If she chooses 1, then N becomes 3. N becomes 3. Bob can only choose 1. If he chooses 1, then the number becomes 2. Alice chooses 1, then the number becomes 1, and Bob has no choices. Well, there's a point at which we should just do something else. And I think if it's N... N equals 4, the person should definitely choose 1. Here Bob chooses 1. Here Bob chooses 1 and he loses. And what's the correct? N equals 32. Alice chooses 16. There's no other choice for her here. Unless she should have chosen 8. Yeah, I don't think this is gonna work. I think we have to look through all the nonsense. Maybe we'll have to come back tomorrow and write something graph-based. Right. I think we'll have to come back tomorrow, write something more graph based. But this is a fun problem though.